Hello, and today we start concrete method, namely primitives of rational functions and today mostly, I guess, we'll consider only algebraic how to say, preliminaries. And I'll start with a lemma, which explains how to divide one polynomial by another polynomial. So that is, suppose P and Q are polynomials of degrees n greater or equal to m greater than 0 respectively. Then there exist polynomials m degree m equals to n minus m and r degree of r less than m such that P of z equals to m of z times Q of z plus r of z. Proof. In fact, today I think most part of assertions will be algebraic, not from analysis, but at least one proof will be from analysis. But these are, of course, algebraic things. But the proof, it's better to do by induction. So, by induction. Suppose the lemma is proved for arbitrary polynomial P of degree less or equal to k. Let us prove the lemma for P such that degree of P, which is n, equals to k plus 1. So now we suppose that the degree n is just degree k plus 1. Okay, so let's write P of z. Let's say it has degree n, so z power n plus a n minus 1 z n minus 1 plus so on plus a naught, and also Q of z is bn m z power m plus b m minus 1 z m minus 1 plus so on plus b naught. And what we know that both a n not 0 and b m not 0, since they are polynomials of precisely degrees n and m respectively. Now consider P1 of z equals to P of z minus a n over b m times z to the power, which power, I think n minus m, right? Yeah, n minus m, yeah, and times q of z. Let us think about the degree of this polynomial. So what is it? This has degree equals to n, right? That polynomial, let's have a look. What is the degree of that polynomial? So we multiply q of z, right, by z to the power n minus m. It means the highest degree is now n, right? So it means this polynomial has degree equals to n as well. But what is about the leading coefficient? So here this is a n z power n. What is about that one? A n over b m z power n minus m times b m z to the power m. So what happens? We cancel bm, cancel m, and we see the same term, right? With highest degree. Terms with highest degree are the same. And it means the degree of our polynomial P1 is strictly less than n. That's for sure. Then what can happen? There are two possibilities. So first case, which is easier, if the degree of our polynomial is strictly less than m, then we stop. Why? Because then R of z equals to just our P1 is suitable. Why? Look, because we have M of z equals to an over bm, okay, z to the power n minus m. Yeah. Because look what we have. P of z equals to m of z times q of z plus r. Precisely what we want. Precisely what we want, right? So our first case is done. Second case. If the degree P1 is greater or equal than m, let it be k. Let it be k. So what it means? It means that we can apply our supposition, right? Polynomial P1 has degree, better to say less or equal than k, right? Less or equal than k, because k is equal to n minus 1, we suppose. K equals to n minus 1. So, degree of our polynomial is for sure less or equal than k, because this is less than n. Hence, degree of P1 less or equal n minus 1, what is precisely k. So, we have a polynomial of degree less or equal than k. And by supposition, by induction supposition, we suppose that our lemma is proved for arbitrary polynomial of degree less or equal than k. So, by induction hypothesis, by the induction hypothesis, what we have? We have, there exists a polynomial, let's say m1 of degree m1 equals to, okay, I don't know what is degree of P1, doesn't matter, degree of P1 minus m, and R1, there exists R1, degree of R1 strictly less than m, such that P1 of z equals to m1 of z, q of z, plus R1 of z. Thanks. Degree of P1 less than m. Because, look, what we have proved. Our polynomial P1 is a difference of two polynomials of degree n, and the leading coefficient, leading term, better to say, with z to the power n, we computed just now, right? And the coefficient is 0, and it means the leading coefficient, I mean, if we consider P1 as a polynomial of degree n, the leading coefficient is 0, and it means the degree of polynomial P1 is strictly less than n. That is what I computed, yeah, here, coefficient in z to the power n. Okay, I hope it's okay. Yeah, okay. So, then look, if we substitute this expression for P1 into our formula, then what we have? We have what we want to prove with, so we have capital M of Z equals 2. Let me collect all those terms, and we obtain an over bm z to the power n minus m plus m1 of z. That is capital M of z. And R of z. What is R of z? If we substitute, yeah, in fact it's nothing else but just our R1. Same. Yeah. So look, if we substitute this expression to P1, P of z equals 2. So degree of R1 less than m, it's okay, right? And what is about degree of capital M? Degree of M1. Look, degree of M1, degree of M1. Degree of P1 minus M is strictly less than n minus m, right? So M1 has smaller degree than that one, and here we have precisely degree equals to n minus m. So degree of m is indeed equals to n minus m. So the lemma is proved by induction. And how it works, I hope you know. If you don't know, then that is just to repeat. So example, how this lemma works. Let P of z be, let's say, 2z power 4 minus z squared plus 1, and Q of z is z cubed plus z. So what we do, we just divide one polynomial by another. Like, I hope you know how to divide numbers. That is precisely, it looks like division of numbers. So we want to divide this polynomial by that one. And we look only onto the leading terms. Leading terms. So we divide 2z power 4 by z cubed. What is the result? The result is 2z. After that, what we do? We multiply denominator by 2z. What we obtain? 2z power 4 plus 2z squared. Right? Yeah. Then we subtract what we obtain, minus 3z squared plus 1. The degree of this polynomial is strictly less than 3, so we are done. What we obtain, in fact, we obtain the following representation. Z squared plus 1 equals to 2z times z cubed plus z plus the remainder, that is the remainder, minus 3z squared plus 1. So what we have here, m of z, the result of division is 2z, entire part, and remainder is r of z. The degree of r is strictly less than 3. Degree of m is equal to the difference between degrees of our polynomial, right? Okay, now let's apply this lemma to obtain Bazoo theorem. And I don't know how to write Bazoo in French. Theorem. I hope I am not mistaken, but I am not sure. Bazoo theorem. I don't remember. Okay. So, if Z0 is a zero of a polynomial P of Z, then P of Z equals to Z minus Z0 times Q of Z, where Q of Z is a polynomial and degree of Q equals to degree of P minus 1. Proof. We apply the lemma with so apply lemma 1 with P of Z equals to P of Z and Q of Z in lemma equals to Z minus Z0. So degree of Q is 1, and it is certainly less or equal than degree of P. Why? Because if Z0 is a zero of a polynomial, then for sure a polynomial has degree greater than 1 of a polynomial, okay, maybe non-constant, let's say, right? Of a non-constant polynomial. Non-constant polynomial. Bazoo, thanks. Yeah, thanks. I forget how it is written in French. Okay. Non-constant, yeah, because otherwise, if P of Z is identically 0, then of course it's not true. Okay, so yeah, and if we apply lemma with those data, then there exists M and R such that P of Z equals to M of Z times Z minus Z0 plus R of Z, where degree of R is less than degree of Q, so it's less than 1. What means degree of a polynomial strictly less than 1? It means degree equals to 0. No other possibilities. So it means, in fact, R is a constant. R is a constant. But now what we can do? We can substitute. Z equals to Z0. And what we obtain? P of Z0 is 0, right? And if we substitute here z equals to z naught, this bracket equals to 0, what remains? Just our constant r. So we have r equals to 0, right? And it means there exists a polynomial, so no r. We have precisely the same expression as we wanted with capital M. Okay, now as q of z in theorem, we should take m of z from the lemma, right? That is, the proof is over, right? Okay, now one more lemma. In fact, it should be proved in chapter 2 when we considered complex numbers. By the way, I didn't mention here that that is a complex number because both results, I mean lemma and theorem 1, they are valid in both cases. Either polynomials are real polynomials and we are talking about real zeros and nothing else, right? Or we are talking about complex polynomials and complex zeros. Both results are valid in both settings. So lemma 2, that is about complex zeros of real polynomials. So if z naught equals to x naught plus I y naught not equals to 0 is a zero of a polynomial p of z, no, non-constant, of a non-constant here, non-constant, constant polynomial p of z with real coefficients, then z naught bar is a zero of p of z as well. Okay, so let's prove this result. Proof. Apply Bazoo theorem. So we can write p of z equals to z minus z naught times q of z. Now take complex conjugate. So we have p of z conjugate equals to z minus z naught conjugate times q of z conjugate. Let's have a look at what is written here. P of z was a polynomial with real coefficients. And what we know about complex conjugation? When you take complex conjugate to a sum or to a product, then you can put conjugate on every term of the product or on every term of the sum, right? So conjugate is taken term by term. Now, look. P of z was a polynomial, not here. Let's say a n z to the power n plus so on plus a naught, right? So if we take conjugate, and remember that all coefficients are real, complex conjugate to a real number is the same real number, right? So it doesn't change. So we obtain a n z bar to the power n plus so on plus a naught. So conjugate will be only over z's, right? Only variable z. So what we obtain, I can write it as just p of z bar. So we just substitute into polynomial p, instead of z, we substitute z conjugate. So let me rewrite it now. P of z conjugate equals to, here I can write also like that. And what is it? For q, it's another story. That is some polynomial, I don't know. In fact, it has degree n minus 1, so b n minus 1, z n minus 1 plus so on plus b naught. And if we take a conjugation, then what we obtain? We should put complex conjugation over each term, right? And I'll denote it by new polynomial, let's say q bar of z bar. So what is q bar? It's a polynomial such that every coefficient is replaced by complex conjugate. So we take conjugate over each coefficient. And we substitute into this polynomial also conjugate, right? So that is new polynomial. So I'll put it here. Now let's have a look at this equality. We have an equality for polynomials where we took as a variable z conjugate. So let us denote w by this z conjugate. So what we obtain then? I have p of w equals to w minus z naught conjugate times q bar of w. What it means? It means that we have z naught conjugate is a 0 of p as well, right? So if we substitute w equals to z naught conjugate, we have 0 in both sides. So theorem is proved, right? Okay. Now the main result of this section is so theorem 2 is called the fundamental theorem of algebra. Every non-constant polynomial with complex coefficients, of course. We don't consider others. With complex or real coefficients, doesn't matter. We don't consider other polynomials. has at least one complex zero. Of course, real zeros are also P of Z conjugate is not like P conjugate of Z conjugate. That is, yeah, that is precisely what I wanted to prove here, yeah? So, because coefficients are real, so conjugate disappear here. That is why we don't write P conjugate of Z conjugate. That is precisely because of real coefficients of P of Z. That is the first question. And second question, in the end, the conjugate of Z naught is a 0 P of W. But that is notation of variable. Notation of variable is W, right? So we have Z naught conjugate is a 0 of P, polynomial P, nothing else, right? Doesn't matter how we denote the variable, W or Z. Okay. Okay, so let me emphasize once again. Here it is written at least one complex zero. It may be that a real polynomial has real zeros only, right? All zeros are real. So we consider real numbers as a subset of complex numbers. So every real number is a complex as well. Because look what is written here. That is a complex number, right? But what was important, integer part was not 0. But if integer part is 0, then complex number is real. Yeah, so real numbers are particular case of complex numbers. Remember about it. That is why when it is written here one complex zero, it may be real. Maybe. But we cannot guarantee that even real polynomial has at least one real zero. That's not true, as we know, let's say, x squared plus 1, right? Real polynomial has no real zeros. But for complex, that's not the case. So every non-constant polynomial with, in fact here, it would be better to omit this sentence. So every non-constant polynomial has at least one complex zero. That's the best formulation of this theorem. And what's about proof? In fact, there will be very short proof in complex analysis course, but complex analysis will be in third year, so quite a long time, right, ahead. And there are proofs purely algebraic, but they are rather complicated. And there is not so complicated proof, but it uses properties of limits of complex numbers, let's say. So I'll give you this proof now, but rigorously speaking, I'll use properties of limits which were proved before for real numbers. And I'll consider instead of real numbers complex numbers. Right? So rigorously speaking, the proof cannot be considered as correct, since I said nothing about limits of complex numbers before, in fact, right? We considered only limits of real numbers. But suppose that you proceed in completely analogous way as we did for real numbers, then you will obtain precisely what we need in the proof. That is, so the proof is not correct at the moment since we didn't consider limits of complex numbers yet. But it will be considered later. In fact, I think next year we'll consider it. After that, the proof will be correct. But at the moment, it is not correct yet. But I don't want to give that theorem without proof. That's the reason why I prefer to give it. Okay, let's have a break. So, proof by contradiction. Suppose there exists a polynomial P of z without zeros in C, and degree P is equal to n greater or equal than 1. So let me write down that polynomial. And in fact, I can consider it as a monic polynomial. So, do you know what is monic polynomial? No? Okay. That maybe doesn't matter. Okay, let it be arbitrary. So, an z power n plus an minus 1 z power n minus 1 plus so on plus a naught. And an not equals to 0. Okay. So we suppose P of z not equals to 0 for all z in C. So it has no zeros, no complex zeros. It's never 0. Okay. Now put eta equals to infimum over all complex numbers z of modulo P of z. That is a non-negative number. Why? It exists. Why it exists? Because look, we take modulus of a complex number, right? That is a real non-negative number, and moreover, since we know polynomial is not 0, then for sure all those real numbers are positive, right? So it means when we vary z in the complex plane, all those numbers are real positive numbers. And of course, arbitrary non-empty set of real positive numbers has an infimum. But it might be 0. That's important, of course, right? We cannot exclude it from the beginning. Okay, now let us rewrite our polynomial in the following form: an z to the power n times 1 plus an minus 1 over an 1 over z plus so on plus a naught over an 1 over z to the power n. And now, first time when there is a thing which is officially not known to you, namely, look, I want to look at the limit as z tends to infinity. We didn't consider complex infinity yet, right? But it's easy to understand what is it. If modulus is infinite, then z tends to infinity, right? Officially, there was no definition, but clearly 1 over z tends to what? 0, right? So every term, and we have finitely many terms, tends to 0 except to this one, right? So it means this term of the product tends to 1 as z tends to infinity. Better to have a look at the first part. This tends to what as z tends to infinity? Look. This tends to 1, doesn't matter, forget about it. And this part tends to what? Infinity, right? And it means that there exists r greater than 0 such that for all z with modulus z greater than r, the limit, so it follows the limit as z tends to infinity, p of z equals to infinity. That is what I need. That is what I need. Otherwise, I'll get a problem. That is what I need. So the limit is infinity, and it means it will be sufficiently large, and I want it to be larger than eta plus 1. That is what I need. Eta is a number, non-negative number, and I know the limit is infinity, so the modulus will be as large as I want, right? Of course, here I refer to some properties of limits for complex numbers, and I'll refer just to intuition. So if complex number tends to infinity, then it will be sufficiently large when z is sufficiently large, right? If p of z tends to infinity, then p of z will be sufficiently large for sufficiently large in modulus z. That is, intuitively it's clear, right? But officially, of course, there was no definition. Okay, that is a property which I need. Now, look, what can I say about infimum of z and c p of z? If modulus z greater than r, then p of z is greater than eta plus 1, right? So it means this infimum coincides with infimum of p of z for z in modulo less or equal than r. So, look, what I know. If z is greater than r, then for sure this number is greater than eta plus 1, right? So it means that infimum which is equal to eta is attained somewhere for modulo z less or equal than r, because for other z it will be essentially greater. By properties of infimum, it's clear. Now, look. Once again, I'm using something what was not proved, but it's analogous to a real thing. What we know, modulo of z less or equal to r, replace z by x. That is the interval, right? From minus r to r. We know that is a compact. Continuous function, model of polynomial is continuous function. Infimum is attained. There is a point where it is precisely equal to infimum. That is what I am using here. P of z naught, where z naught is less or equal than r. So I use property which was proved. Continuous function on a compact attains its maximum and minimum, right? There was such a property. Of course, here it was proved for real intervals. Now I have complex set. That is not rigorous, definitely, right? But I refer to an analog for complex numbers, which will be proved later. Okay, P of z naught is obtained, and then look, that is not zero, we know, right? Because the polynomial is never zero, we supposed from the beginning. And remember, eta, we could not exclude eta equals to 0 from the beginning, right? But now we are sure eta is strictly positive. So eta is strictly positive. That is the first part, what is necessary for us. Okay. Look what we obtained then. So eta is infimum, and it is equal to the value at z naught, right? So we have for arbitrary z complex number, we have modulo p of z is greater or equal than modulo p of z naught. Why? Because eta is infimum, and eta is precisely that one. Now, and that is not zero, also important thing. Consider a polynomial p1 of z equals to p of z plus z naught over p of z naught. Look, what is about modulo of this polynomial? p1 of z. That is modulo p of z plus z naught over modulo p of z naught. Numerator is the value of our modulus, modulo of polynomial at a point, at a complex point. So numerator is greater or equal than denominator. So the ratio is greater or equal than 1, for sure. For all z, for every complex z, for every complex z. And what is about p1 at 0? Let's compute it. What is it? Substitute instead of z0. P of z naught over p of z naught. That is precisely 1, right? So what we obtain? P1 of z is a polynomial, right? Such that it is greater or equal than 1, and P1 at 0 is precisely 1. And if a polynomial is equal to 1 at 0, we can represent it P1 of z equals to 1. Okay, I think I should put here minus, let's say bk z power k, and plus so on, plus bn z power n. P1 is a polynomial of degree n, since we took polynomial of degree n divided by a number, non-zero number. And look, so I should start from 1, right? Because at 0 it should be 0. And what is k? K is minimal integer, minimal degree of z in P1 of z minus 1. So we take P1 of z, it is 1 at 0. If we subtract 0, we have 0 at 0, right? So it starts from a degree, and that is the minimal degree here, right? Okay, so plus, here I should take plus. So bk is not 0, bk is not 0, and also bn is not 0, since we have a polynomial of degree n. Okay, and remember that P1 of z is always greater or equal than 1. Now next idea is the following. I think here I should take minus. I remember somewhere I should take minus. Yeah, here I should take minus. So, denote by C a complex number, by C a complex number such that C power k equals to minus 1 over bk. So kth root, look, that is a complex number, right? Complex number. Bk is not 0. That is a complex number, so we can consider kth root of this complex number. There are many, but it doesn't matter. At least one there is, right? Now, one more notation. I should consider polynomial P1 of Cz and let it be, so I will denote it Q, let's say. Q of z is equal by definition P1 of Cz. Let's understand what is it. So, I want to substitute here instead of z, c, z. What we'll obtain here? C to the power k times z to the power k, right? And c to the power k times bk is minus 1. So, that is 1 minus z to the power k. Other coefficients, I don't care about them. Just, let's say, c k plus 1, z power k plus 1, plus so on, plus c n z to the power n. I don't care about other coefficients. Okay? So, we just substitute instead of z, c times z. And c we choose in such a way that c to the power k times bk is minus 1. So, I wanted to create minus here. Now, look, what is going on? Consider this part, ck plus 1 z to the power k plus 1 plus so on plus cn z to the power n. If we divide it by z to the power k, then what is it? That is c to the power k plus 1 times z plus so on plus cn z to the power n minus k. What is about limit as z tends to 0? Once again, something what was not officially considered before. What is the limit as z tends to 0 of this expression? What is the limit of this expression as z tends to 0? Finitely many terms. Every term tends to what? 0. What is the result? 0, of course, 0. That is 0. So, I will write limit of modulus of this expression. Let me rewrite it once again like that. Is 0. And it means that for sufficiently small z, it will be okay. There exists rho positive such that for all z modulo z equals to rho, we have modulo ck plus 1 zk plus 1 plus so on plus cn z power n less than 1/2 times modulo z power k. So, for sufficiently small z, in particular with modulo z equals to rho, where rho is sufficiently small, it will be less than 1/2. Right? Then, what it means? Look, what happens for z equals to rho then? Look, if we take z in modulus equals to rho, then what is about q of z? Q of z is less or equal modulo 1 minus z power k plus this modulus which is less or equal to, okay, I will write like that, plus 1/2 times z to the power k. And that is valid for arbitrary z in modulus less than rho. And let me consider a particular case. So q1 of rho, just of a real number rho. What is it? 1 minus rho to the power k. In fact, I can, you see, z tends to 0, right? It means rho is sufficiently small. So I can take from the beginning rho smaller than 1. So 1 minus rho to the power k, I substituted z equals to rho to the power k less than 1, plus 1/2 modulo z is rho to the power k, and what is it? That is 1 minus 1/2 rho to the power k. That is strictly less than 1. And look what it means. Let me rewrite it in terms Q is P1 of Cz, right? So what we obtain? Let me rewrite. P1 of C times rho, right? That is Q1 of rho. Is strictly less, that is a real number, belongs to R, right? And strictly less than 1. In fact, it is even positive, right? So I can put here plus, right? It's positive, look. Q1 of rho is a positive number, right? Because we took positive number plus positive number. So it is positive number. So we have a real positive number which is less than 1. And it means, in particular, that model of P1 of C rho is less than 1. And 1 was P1 of 0, right? Remember now what was supposition. Modulo P1 of Z in modulus greater or equal than 1 for arbitrary Z. And we have found a value, 0, where P1 in modulus is less than 1. Contradiction. And that's all. The proof is over. Of course, you can say it's rather complicated, right? Definitely it is very complicated, but if you will consider other proofs which can be in principle considered in first year calculus, then you will understand that is the only possible proof of this assertion at the moment. And how we'll use this assertion? Look, now, corollary. Every polynomial with real coefficients can be represented as P of Z equals to, okay, let me write P of X, leading coefficient times X minus A1 power R1, so on, no, alpha 1, X minus A R alpha R, X squared minus B1 plus B1X plus C1 power B to 1 times so on times X squared plus BSX plus CS power beta S, where Bj squared minus 4Cj less than 0, j equals to 1, so on, S, and alpha j's and beta j's are natural numbers. So that is an expansion of arbitrary real polynomial into linear terms and quadratic terms. Those quadratic polynomials are irreducible. Why? In real numbers. Because discriminants are negative, right? So no real zeros for every bracket. And why? How we can do it? We apply Bazoo theorem. We know by the fundamental theorem of algebra that there is at least one complex zero, right? Take this complex zero. If it is real, then we apply Bazoo theorem and we obtain x minus this real zero times a polynomial of degree smaller than p, right? Once again, we apply the fundamental theorem to new polynomial. There is a complex polynomial of this u, and we proceed further and further. In this way, we'll consider all real zeros, right? After that, it may happen no more real zeros. But according to the fundamental theorem of algebra, there is at least one complex zero, while the polynomial is not constant, right? If a real polynomial has a complex zero with non-zero imaginary part, then the conjugate is also a zero, right? And we multiply z minus z naught times z minus z naught conjugate. What is it? If I substitute z minus x naught minus I y naught, z minus x naught plus I y naught, and it gives the following. It gives the following: z squared minus x naught squared minus I squared. I'll write it better, shorter. Z minus x naught squared minus I squared y naught squared, right? That is z squared minus 2x naught z plus x naught squared plus y naught squared, right? Because I squared is minus 1. And you see, that is precisely C here, C1, and that is B1. And look, if you take B1 squared, that is strictly less than, because what is B1 squared? B1 squared is minus 2x naught squared, 4x naught squared. That is strictly less than 4 times x naught squared plus y naught squared. What is 4c1? Why it is strictly less? Because we suppose y naught is not equal to 0, right? We had complex 0 with non-zero imaginary part. So, what it means? It means that once a polynomial has a real polynomial has a complex 0 with non-zero imaginary part, then you can divide it by quadratically reducible polynomial of this form, right? Here it is, right? Once again we divide, we get a polynomial of smaller degree, and we proceed and proceed and proceed, right? And we proceed up to the moment when we'll obtain constant, right? So while we have a non-constant polynomial, we can find a 0 by Bazoo theorem, divide, and continue until we obtain a constant. That means that finally we'll obtain a representation, an expansion of a polynomial into linear and quadratic irreducible terms. That is the main result of what we'll need for the future. Okay, that's all for today. Definitely, I'll not ask you the proof of the theorem. It was given just for your information. What should we do to understand today's lecture? Oh. There is a question, what should we do to understand today's lecture? If the question is about the proof of the fundamental theorem of algebra, then the answer is nothing to do, because you don't need to learn this proof and to understand. That is just for the best of you who will want to understand what is going on with it. That's all.